So friends, till now we have looked at three questions, two theoretical and two numerical and one theoretical. Now we will see this question. A large flat plate is exposed to an air stream moving at 30 meters per second at 25 degrees Celsius and 1 atmospheric pressure. Experimental data shows that water evaporates from the plate surface at a mass transfer coefficient of 1.8 into 10 to the power minus 2 meters per second. The Schmidt number for the system is zero point 0.6 and the Prandtl number is 0.72. Using the heat and mass transfer analogy, determine the first part of our question, the heat transfer coefficient in watt per meter square Kelvin if the thermal conductivity of air is 0.028 watt per meter Kelvin. And the second part, the convective heat flux if the plate is maintained at 80 degrees Celsius. So let's look out what values are given in the question already. The first, the characteristic velocity, which is 30 meters per second. We usually take the bulk velocity of the fluid as the characteristic velocity. So we have taken the characteristic velocity in our question as 30 meters per second. The mass transfer coefficient has already been given as 1.8 into 10 to the power minus 2 meters per second. The Schmidt number value is 0.6 and the Prandtl number value is 0.72. So now we move to our first part. So now before moving to the first part, let's once again understand the question. We have been given a large flat plate which is exposed to an airstream moving at 30 meters per second. So we have been given the bulk velocity of the airstream which is moving at 30 meters per second at 25 degrees Celsius and 180 atmospheric pressure. Now, and also we have been told that the water evaporates from the plate surface at a mass transfer coefficient of 1.8 into 10 to the power minus 2 meters per second. So we have been given the Schmidt number and Prandtl number and also the mass transfer coefficient. So now from this question we understand that we have to use the heat and mass transfer analogy, and we have been given the data of mass transfer, and now we have to calculate the data for heat transfer, that is the heat transfer coefficient, and also we have to calculate the convective flux for which we need the heat transfer coefficient, and this is where our analogies comes to our help. So we look at our first part of the question. Here they have asked heat transfer coefficient H in watt per meter square Kelvin, and they have already given the value of thermal conductivity of air which is 0.028 watt per meter Kelvin. If we look at the question, we don't need to convert any units as already the units are consistent. So we move to our first part. The thermal conductivity is 0.028 watt per meter Kelvin. The density of air we assume as 1.18 kg per meter cube. The heat capacity of air we take as 1005 joules per kg Kelvin. Now we will use Chiltern-Coulomb relation again in this question. Now when to use Chiltern-Coulomb relation instead of Reynolds analogy? The first condition can be when Prandtl number is not equal to Schmidt number. The Chiltern-Coulomb analogy is useful when the Prandtl number and Schmidt number are not equal, which is often the case in many practical fluid flow situations. For example, water has a much higher Prandtl number than air, while gases typically have a much lower Schmidt number than liquids. The second condition is wide range of flow conditions. Unlike the Reynolds analogy, which assumes a close relationship between heat and mass transfer, the Chiltern-Coulomb analogy can be applied to both laminar and turbulent flows with different fluid properties. Third condition can be non-ideal conditions. In cases where the flow is not perfectly turbulent or the heat and mass transfer mechanism behave differently, example high temperature differences or significant changes in the properties of fluid, the Chiltern-Coulomb analogy gives a more accurate representation of the relationship between heat and mass transfer. So we look at our equation, that is standard number of heat transfer into Prandtl number to the power 2 by 3, which is equal to the standard number of mass transfer into Schmidt number to the power 2 by 3. We substitute our formulas of standard number, which is heat transfer coefficient average value upon density into heat capacity into characteristic velocity into the Prandtl number. Prandtl number is given as viscosity into heat capacity upon thermal conductivity whole to the power 2 by 3, which is equal to the standard number of mass transfer, which is given as mass transfer coefficient average value upon characteristic velocity into the Schmidt number, which is given as kinematic viscosity upon diffusion coefficient whole to the power 2 by 3. Now putting the values of the which we are given in the question of density, heat capacity and the characteristic velocity, Prandtl number, Schmidt number and mass transfer coefficient, we get our heat transfer coefficient as 18.903 watt per meter square Kelvin. Now since we have got our heat transfer coefficient, we will now do the second part of our question, which was to calculate the heat flux, and we have been given our surface temperature as 80 degrees Celsius. We will convert the temperature given in Celsius into Kelvin. So we will use the equation of heat flux as heat transfer coefficient average value into the temperature difference. So the surface temperature is given as 80 degrees Celsius, which we will convert it into 353 Kelvin, and the T infinity, which is the bulk temperature of the air at infinity, we will take which is given in the question is 25 degrees Celsius, we will take 298 Kelvin. Now when we put these values in the equation of heat transfer coefficient and the temperature, we get our heat flux as 1039.66 watt per meter square, which is calculated by Q is equal to H average value into Ts minus T infinity, which is we will take H as 18.903 into Ts, which is 353 Kelvin, minus T infinity is 298. So the Q, the heat flux we got was 1039.66 watt per meter square. So now we have completed our fourth problem, and now we will move ahead to our final problem. So now let's discuss our final problem. The problem reads out as: a flat plate is exposed to an air stream at 25 degrees Celsius and 1 atmosphere pressure, moving at 40 meters per second. The plate is maintained at 80 degrees Celsius. The heat transfer coefficient for this system is 150 watt per meter square Kelvin. Now, if a volatile liquid is evaporating from the surface of plate in the same air under identical flow conditions, the mass diffusivity of vapor in air is 2.5 into 10 to the power minus 5 meter square per second, and the Schmidt number is 0.62. We have to calculate the first part, the mass transfer coefficient for the evaporating species. Second part, the mass flux, or if the surface vapor concentration is 0.02 kilomole per meter cube, and the free stream concentration is 0 kilomole per meter cube. So what's happening in this question is a flat plate is exposed to an air stream. The temperature of air stream is 25 degrees Celsius and 1 atmospheric pressure, and the bulk velocity of the stream is 40 meters per second. The temperature of the plate is given as 80 degrees Celsius, and the heat transfer coefficient for the system is given as 150 watt per meter square Kelvin. A volatile liquid is present on the surface of the plate, which is evaporating under the same conditions. The mass diffusivity of the vapors in air is also given, which is 2.5 into 10 to the power minus 5 meters square per second. And we have also given the Schmidt number as 0.62. So if we look at this question and compare with the last question, we will see that we have to calculate over here is mass transfer coefficient, and in the previous question we had to calculate the heat transfer coefficient. Here the heat transfer coefficient has already been given, the values are given, and we have to calculate the mass transfer coefficient. So this is where the Chiltern-Corbin analogy will help us again to relate these terms and calculate the value of mass transfer coefficient. And another reason to use Chiltern-Corbin relation is because the Prandtl number and Schmidt number are not equal to 1. So now, before solving the question, let's look out our given data again. The heat transfer coefficient 150 watt per meter square Kelvin, diffusion coefficient 2.5 into 10 to the power minus 5 meter square per second, Schmidt number as 0.62, Prandtl number as 0.7, heat capacity as 1005 joule per kg Kelvin, the characteristic velocity 40 meters per second, and density rho 1.184 kg per meter cube. So from Chiltern-Corbin analogy, we know the relation standard number of heat transfer into Prandtl number to the power 2 by 3, which is equal to standard number into mass transfer into Schmidt number to the power 2 by 3. Now if we put the formulas of each of these dimensionless number, first the standard number of heat transfer, which is heat transfer coefficient upon density into heat capacity into characteristic velocity V, into the Prandtl number to the power 2 by 3 equal to the standard number of mass transfer, which is mass transfer coefficient upon characteristic velocity V into Schmidt number to the power 2 by 3. So if we further do the relation, solve the relation, we will cancel the term of characteristic velocity on both sides, and we will rearrange the equation to give us the value of mass transfer coefficient. Now we substitute the values of the terms we have been given. In the final relation, which is given as Km is equal to heat transfer coefficient H upon density rho into heat capacity Cp into Prandtl number upon Schmidt number whole to the power 2 by 3, where H is 150 upon density rho 1.184 into the heat capacity 1005 into the Prandtl number our Schmidt number, which is 0.7 upon 0.62 whole to the power 2 by 3. If we solve the equation, we will get the value of mass transfer coefficient as 0.1366 meters per second. Now we will move ahead to our second part of the problem, which is calculating the mass flux. In the second part, we have been already given the concentration near the plate and at the bulk, which is the concentration at near the plate is 0.02 kilomole per meter cube, and at the bulk it is 0. So we will use the relation of Na is equal to mass transfer coefficient into difference in concentration, the Ca at the surface minus the Ca at the bulk. So now if we will substitute the value of mass transfer coefficient which we got from the previous part of the question, that is 0.1366 into delta Ca, which is Ca at surface minus Ca at infinity, that is at the bulk, as 0.02 minus 0. So when after substituting these values, we get the final answer of the mass flux as 2.733 into 10 to the power minus 3 kilomole per meter square second. So now we have looked at all the 5 questions where we have used Chiltern-Colburn analogy differently. Like first, we have to get the heat transfer coefficient from the mass transfer coefficient and the values of mass transfer, and in some case the heat transfer coefficient was given and we have to calculate the mass transfer coefficient.
So guys, after having a look at all the questions, let's get back to square one of why, what we had to study, and the motive of this video was. We wanted you to understand what are analogies, what is the physical significance, what are its applications, and why do we have to study them as chemical engineers. We had a look at various numerical questions as well as theoretical aspects of the same. Now let's quickly have a quick recap of the same. As I said earlier, in chemical engineering, analogies play a crucial role, especially in transport phenomena, where we deal with momentum, heat, and mass transfer. One of the most famous analogies, which is the Reynolds analogy, which draws a parallel between momentum and heat transfer in turbulent flow. But we did not use it because in most of the practical application cases, Chiltern-Colburn analogy is used in industries, since it deepens the connection of all the 3 processes, which is mass transfer, heat transfer, and momentum transfer. By using these analogies, we could simplify mathematical models, we could make reliable predictions and optimize industrial processes. We had a look at numericals which were majorly of real life applications. Also, the similar concepts are used in industries on a large scale. Analogies like these help us relate various terms and help in solving various problems. As we discussed earlier, the applications, which again have given and shown us its uses, like simplifying design equations, optimizing industrial processes, reducing experimental effort, and enhancing process control and efficiency. So guys, by using these Reynolds and Chiltern-Colburn analogies, engineers can develop simpler, cost-effective and efficient solutions for problems involving momentum, heat and mass transfer, making them indispensable tools in chemical and process industries. This video was a part of initiative taken by me, Tejbir Singh, and Vedant Tarone as a part of our Transport Phenomena mini project from VNIT. Our enrollment numbers are PT22 CME 090 for me, that is Tejbir, and PT22 CME 111 for Vedant. We thank all the people who have supported us in making this by not only helping us in resources but also guiding us. Thank you for having a look at our videos. I hope you found this useful or it helped you in any possible way. Thank you so much and have a wonderful great day ahead. Cheers to learning.